don't fall asleep. We'll leave the lights off. And with the lights off, if you watch the video like this week and you can't see this because the lights are off, let me know. We'll fix it. Today's lecture is not really all that much about chemistry. It's about math. Yes, math. You all hate math. You, good. Good. Did you pass Calc?
Yes, I got it.
Okay. That's an important differentiation. If you pass Calc, the math we do in here is going to be very easy. The hardest math we do in here is solve for X algebra. Okay? That's the hardest math that we do. But we do lots of different types of math. The math itself is just numbers, but how we deal with them changes a lot. And so today we're going to deal with some very basic math that we're going to use throughout the semester. Then we're also going to talk about measurements. Because in chemistry, everything that we do in the lab involves measurements. Either we're weighing something out, we're measuring how much volume we have, we're seeing how hot something is. Everything is a measurement. That's how we quantify, put numbers to the things that we deal with. We measure them. So we're going to talk about them. So the first slide explains to us why we have to worry about measurements. And in terms of measurements, we're going to talk about units. Every number in this class, with two exceptions, and I'll point them out when we get to them through the entire semester, every number has to have a unit. And a unit is like an inch or a pound or a meter or something like that. And you have to be comfortable with your units, otherwise you ruin a $125 million Mars orbiter. Because one team used inches, the other used centimeters, and they didn't convert them correctly. And so the parts didn't fit together, or part of their calculation of where they have to shoot the orbiter to actually hit Mars didn't work. And they ruined a $125 million orbiter because of units. If you get units wrong, it's not going to cost you $125 million, but it will cost you points. Okay? When you start to get graded papers, hard copy papers back from me, I have a series of stamps that I stamp when you get something wrong. And one of them is units. If you get your units wrong, you're going to get a stamp. Okay? The other one is sig figs, which we're going to talk about today. If you get your sig figs wrong, you get a stamp. And if you clearly looked up an answer online, you get a stamp. Okay? So these are some examples of units. In science, we have what we call the SI units, the International System of Units. Every type of measurement that you would do has what's considered the standard measurement. And this was decided by some people sitting around who knows where, drinking who knows what, and they decided. Even though a lot of these units are the units we're going to use, in some cases they aren't the most realistically practical. They're not real world practical. For math, in most cases, we're going to be working in grams, not kilograms. And length, we'll be dealing with mostly centimeters, because centimeters is about that big. You don't measure small things in meters until that big. And so you don't have to memorize these. We'll go through them all. But looking through meter, kilogram, liter, seconds, you've probably seen those four. But temperature, you immediately think Fahrenheit, and you certainly know Celsius. But in science, in most cases, we use something else called kelvins. And then the weirdest one, which is going to bug you for the rest of the semester once we start doing it in a month or so, is a mole. We're not going to talk about moles yet. You got a month or so. When we do measurements and we use these SI units, we add prefixes to them. Because you've seen kilograms, you know grams, you know meters in kilometers, in centimeters, in millimeters. These prefixes just tell us what the power of 10 is compared to the base unit. This is a length measurements. You have gigameter, megameter, kilometer, centimeter, millimeter, and so on. And this table is mass. Gigagram, megagram, kilogram, centigram. So if I go back and forth, what do you notice is different? Oh, it's really slow today. What's different between these two? What's the only thing that changes?
The
only thing that changes for mass, we have a G here. And for length, we have an M per meter here. The prefixes stay the same. Centi always means 10 to the negative 2. And 10 to the negative 2 is 1/100th. So a centimeter is 1/100th of a meter. A centigram is 1/100th of a gram. Kilogram is 10 to the third. 10 to the third is 1,000. So a kilogram is 1,000 grams. And a kilometer is 10 to the third, or 1,000 meters. So we have these prefixes, and that allows us to take our SI unit and deal with a huge range of values. Because we can go all the way from pico, which is a trillion, all the way up to a giga, which is a billion. And all we have to do is keep our M here and change our prefixes. After today's class, after today's quiz, every quiz after that, you'll have a cheat sheet. Okay? On that cheat sheet is a periodic table. There's equations. And one thing that's on there is this prefix table. Okay? So you don't have to memorize this, although I would memorize kilo, centi, and milli, because you're going to use them over and over and over again. So it's going to save you having to look up. A milli is 1/1000th. So a millimeter is 1/1000th of a meter, which means how many millimeters are in a meter? 1,000. Make sure you can look at it two different ways. So a centimeter is 1/100th of a meter, which means that there are 100 centimeters in 1 meter. We'll do an example of a conversion in a minute. So what are we measuring? One thing we have to measure is mass. And when we find the mass of something, what we're doing is we're finding the quantity of matter. If I have a chunk of a rock and I find the mass of it, what I'm going to do is I'm going to find how much matter is in that rock. So we said chemistry was the study of what? Matter and energy. And so mass is a measurement of how much matter we have. It's very, very similar to weight. In real life, we use mass and weight interchangeably, but weight depends on gravity. If I weigh 200 pounds on Earth, do I weigh 200 pounds on the moon? No. Why not? Gravity is different. There's less gravity on the moon. And so to get weight, you take mass and multiply it by gravity. That's not something you have to do. But if that gravity changes, your weight changes. But mass is a measure of the amount of matter. If I weigh 100 kilograms on Earth, that tells you how much matter is in me. If I go to the moon, I didn't lose or gain matter. I am still me. So I'm still 100 kilograms. The SI unit of mass is grams. So you have grams, kilograms, centigrams, milligrams, going off of that. If we want to measure mass, we measure it on what we call a balance. And there are two types of balances. There are electronic balances, which you would probably call a scale. I don't care if you call it a scale or a balance. And then there's also a normal balance, just like the laws, the balance of justice or whatever it is. And then there's also the triple beam balance that we'll use in lab. There's a platform and then some weights that you slide back and forth where your goal is to balance it. Okay? So to give you an idea of the mass of some things, a salt crystal is 50 milligrams. How many milligrams are in a gram? How many? 1,000. A milligram is 1/1000th of a gram, and so there are 1,000 milligrams in a gram. So one tiny little salt crystal is 50 milligrams. The average person is 70 kilograms. That gives you an idea of how much something weighs. Somebody have a bottle of water or something that has a volume on it. How many milliliters are in that bottle? Does it say on the label?
500.
So a normal bottle of water that's 500 milliliters, half a liter, is going to weigh 500 grams. That gives you sort of an idea of the size of these mass units. How many grams are in a kilogram? 1,000. To make it a little bit more difficult, how many kilograms are in a gram? 1/1000th. And so if you want to write that out, now I got a marker out.
Are those markers on the table?
There. So if you wanted to write 1/1000th out, how would I write that? Not in fraction form, decimal form. I got 0.001 and 0.0001. Which one is it? That one. Another thing we measure is volume. You've been calculating volume since you took very basic trigonometry in probably middle school. If you want to find the volume of a box, how do you calculate it? Length times width times height. If you have a box-shaped object, it's really easy. Volume is length times width times height. If we're talking about volume, when we measure length and width and height, we measure them all in centimeters. So I measure that in centimeters, that in centimeters, and that. We get centimeters times centimeters times centimeters, and what we get is centimeters cubed. And so when we're talking volume of a solid object, the most common unit that we use is cubic centimeters or centimeters cubed. A cubic centimeter is the same thing as a cc. cc stands for cubic centimeters. To make it a little bit more confusing though, forgot about the example. What is the volume of that cube?
It's 2 times 2 times 2.
Right. Because it's a cube, all sides are the same size, right? So because we know one side, it's 2, 2, and 2, but 2 times 2 times 2 is 8. 8 what? What is my unit on that volume? Cubic centimeters, yeah. So we have 2 centimeters times 2 centimeters times 2 centimeters equals 8 centimeters cubed. Because 2 times 2 times 2 is 8, and centimeters times centimeters times centimeters is centimeters cubed. When we measure volume of liquids, we have a slightly different unit. We use milliliters to measure a normal volume of a liquid. And it seems like it's a completely different unit. We have cubic centimeters in milliliters. But to make it easier, 1 cubic centimeter is exactly equal to 1 milliliter. That's a little conversion you're going to have to remember. A milliliter in a cubic centimeter is exactly the same thing. So even though we normally use cubic centimeters as a unit for solids, and milliliters as a unit for liquids, you can use them interchangeably. It's going to look weird, but I can give you the volume of this table in milliliters. He can give you the volume of his water bottle, the water in his water bottle, in cubic centimeters. People are going to give you a weird look, but you're perfectly correct. And so all I care about when I grade things is if you're correct, not whether you're weird. So if you want to be weird and be proud of it, okay? A milliliter is the same as a cubic centimeter. How many milliliters are in 1 liter? 1,000. That's another conversion you're going to do over and over and over again. There's 1,000 milliliters in a liter. So here's some examples. We have to convert 25 milliliters to liters. We've got 25 milliliters. Okay, 25 milliliters. We need to convert that to liters. How would you do that?
Write it on the fraction form, and you can put in 25, say 0.0095.
So I heard multiply by 1,000.
Yeah, and divide by 25.
Well, there are multiple ways we can do this.
Well, you have
Okay.
1,000.
And say it again?
You have 1,000 milliliters in a liter, so just, well, you have to put like 1 liter over 1,000 milliliters, so you can cancel out with milliliters.
So the way she wants to do it, she wants to go 1 liter. She wants to do it that way. Okay? When you do it that way, when you put it into your calculator, what do you end up doing with that 1,000? You divide by 1,000. You're not going to multiply by 1,000, you're going to divide by 1,000. And I always stop and think about these problems, because using a little bit of logic, you can figure out, do I need to multiply by 1,000 or do I need to divide by 1,000? What is larger, a milliliter or a liter? A liter is larger, right? So if I'm going to convert milliliters, which are small, to liters, which are big, is my number going to get larger or smaller?
Small.
It's going to get smaller. Because a liter is larger, I need fewer of them to equal the same amount. And so, I'm starting with 25. I know I have to do something with 1,000. I either have to multiply or divide. But I know I need to make my number smaller. So in order to make it smaller, do I need to multiply or divide by 1,000? Divide. And so mathematically, you end up coming out exactly the same at the end. And so it's a matter of using sort of a conversion factor method that we'll do up the wazoo the rest of the semester, including today, or using a little bit of logic in order to help you set it up. Okay? Whichever method works for you, use it. If you get the right answer, that's all that matters. Here we've got another one. We've got 25 milliliters, and we're going to convert to quarts. Do we have a conversion between milliliters to quarts? No. So, if we can't convert from milliliters to quarts, how do we do this? Yeah.
Is
Isn't it like the same as before? You start with the 1 liter over 1,000 milliliters,
And then what?
and then you do 1 liter over 1.057 quart.
Yeah. So we're gonna have to do it in 2 steps, right? We don't know how to go from milliliters to quarts, but we know how to go from liters to quarts. We're given a conversion factor, liters to quarts. And we know ourselves how to go from milliliters to liters. So we can go from milliliters to liters to quarts. So I'm going to convert to liters, and then I'm going to multiply by my other conversion factor. Okay? And so there's the unit canceling way that we're going to use a lot, and then there's also the logic way. So let's start with the logic way. Based on that conversion factor, 1 liter equals 1.057 quarts. What is larger, a liter or a quart? How many say quart?
It's not larger if it equals it.
How many say liter?
Same.
It's not the same.
It says equals though.
No, it's
One liter equals 1.057 quarts. If they were the same,
Oh, I'm
it'd be
sorry,
1 liter
liters
equals.
The liter's bigger.
What?
A liter is bigger. It takes a little bit more than 1 quart to equal 1 liter. So what this is saying is 1 liter is equal to more than 1 quart. I need more than 1 quart in order to equal that 1 liter. So which one is larger? Liter. So if I'm going from liters to quarts, I'm going to have to do something with 1.057. Am I going to multiply or am I going to divide? If I'm going from liters to quarts,
You divide
do I expect my number to go up or down?
down.
Because he's
Up.
more than.
You're going from a bigger thing, liters, to a smaller thing, quarts.
Are you not always trying to get quarts as a smaller number to liter? I mean,
I'm not sure.
liters are bigger than quarts, right?
Yes.
So if you multiply, isn't that going to make the number of quarts more than the number of liters? Then that way, I don't know.
Let's think of it this way. We said a liter is larger, right? And so if I have a measurement in liters, and then I need the same measurement in quarts, I need more quarts in order to get the same measurement.
Okay.
And so my number is going to go up. And so if my number is going to go up, am I going to multiply or divide by 1.057? I'm going to multiply. And so we've got 1.057 quarts is 1 liter. Okay? Yes, the units cancel nicely, and we'll get back to that in just a minute, maybe even in this slide. So when you do that math, you get 25 divided by 1,000 is 0.025. Then you take 0.025 times 1.057, you get 0.0264. Yeah.
Anytime we're doing a quiz or test or anything and there's a written part, like questions like this, how far do you want us to round to really always tell us?
That is coming up today. There are set rules that you're going to absolutely hate. Every fiber of your being that will tell you how to round it. Yeah.
Just quarts, so
Yes, it should be. Nice catch, thank you. So that L should be quarts. So now we've measured mass, we've measured volume. Now we can calculate density. Density is how much mass there is in a certain amount of space. So we calculate density by taking mass and dividing by volume. And so the equation for density is D equals M over V. That's an equation you're going to use over and over and over and over again this semester. It's going to be on multiple exams. It's going to be on multiple homeworks, and it's not on the cheat sheet. Okay? It's also going to be in the lab. We're going to have an entire lab day on density. So memorize that formula. It's not difficult. D equals M over V, DMV. Just be careful. If you remember DMV, it's not that. Some people I see frequently will write that as the equation for density. Don't do it. It's that. D equals mass over volume. Okay? So if we are measuring density of solids or liquids, they're normally pretty high because the molecules are packed close together. And so the normal unit for density is grams per milliliter or grams per cubic centimeter. If we're dealing with gases, gases are very low density because the molecules are spread way apart. Almost everything in a gas is empty space. And empty space has no mass. So in order for our grams number to not be itty bitty tiny, we need a lot of gas. A large number of liters. And so density of gas is generally grams per liter. So these are some examples of density. Like I mentioned, the gases have very low density. Here they're given in grams per milliliter so that you can compare them to solids and liquids. So the gases are very, very, very low compared to the liquids and the solids. In terms of a general pattern, what do you see in terms of density from gas to liquid to solid? There are exceptions, but what's the general trend? It gets bigger. Why? Explain to me at the molecular level why density gets higher as you go from gas to liquid to solid.
Atoms get closer together.
The atoms get closer together. And so imagine you have a box this big, and you're going to pack in as many molecules as you can. If it's a gas, you can't pack them very tightly. So you have a lot of empty space in your box. With a liquid, you can pack them pretty tight. With a solid, you pack them even tighter. So you get more atoms in that box, so that box weighs more. And the formula is mass over volume. The volume is the size of the box. That's not changing. But as you put more atoms in, you get more mass. So as mass goes up, as M goes up, D goes what direction? Up. As mass goes up, it's on the top of the fraction, density is going to go up. If volume goes up and mass stays the same, what direction does density go? Down. Make sure you're comfortable with these algebra relationships.
Can you repeat that?
If mass goes up, density goes up. If volume goes up, density goes down.
Because it's divided.
Because you're dividing by a larger number, so your answer is going to go down. So if mass goes down, density goes down. If volume goes down, density goes up. Basically, mass and density go in the same direction. Volume and density go in opposite directions. So here's our cube again. We're given that the mass of the cube is 11.2 grams. Now we're being asked, what is its density? How are we going to do that? So this is our formula, right? The very first thing when you have a problem that deals with an equation is figure out which you're trying to solve for. Which of these three variables are we trying to solve for? Density. if we're trying to solve for density, that means we have to be given all of the other variables. So, we have to be given mass. What is our mass? It's 11.2 grams. It's given straight to us. 11.2 grams. We have to be given volume. What is our volume? 8 centimeters cubed or 8 cubic centimeters. It's not directly told to us, but we already calculated it. We know it's a cube. We know one side is 2. And so the volume of that cube is 2 times 2 times 2 equals 8 cubic centimeters. So density equals 11.2 grams divided by 8 cubic centimeters. When you put that into your calculator, what do you get? 1.4 what? Grams per centimeter cubed. If you want to be weird, you can be weird. And so it's a density. And so the normal unit we would use is grams per cubic centimeter. But mathematically, it makes sense also. You have grams divided by cubic centimeters. Grams divided by cubic centimeters.
Did you also do grams divided by milliliters?
Yes. We're going to do this in lab in a few weeks, but this is a graduated cylinder filled with a number of different liquids. And clearly they're not mixing, and they're creating different layers. Which of these layers is the most dense? Why?
Because gravity pulls down the heaviest.
Yes. And so this is a matter of where that weight comes in. Gravity pulls on something that's heavier, has more mass, more. So it ends up at the bottom. Which is the least dense? Top one. Test taking hint. If you see a question like this, or in any other subject matter, where it's saying which is the most, which is the least, don't pick one in the middle. Okay? If you have to completely guess, pick either the top one or the bottom. You got a 50-50 chance. Okay? If you pick one in the middle, you're doomed. So here's a person in the Dead Sea. What is more dense, the person or the Dead Sea? The Dead Sea is more dense because the person is floating on top. And so it's just like this, but there's only two things. There's a person and the Dead Sea. So the Dead Sea ends up at the bottom, the person ends up on top. Why does this specify Dead Sea? The Dead Sea is very, very, very high salt concentration. As you dissolve more salt in water, it becomes more dense. And so it's very, very easy to float in the Dead Sea. Has anyone ever heard of it being easier to float in the ocean than it is in the lake?
Yeah.
Yeah. And so that's because the ocean has salt dissolved in it. In the lake, there's no salt, and so the lake is less dense. And so what are we made up mostly of? Water. And so if we're mostly water, our density is going to be very, very close to the density of water. And so the little bit of difference in the density of fresh water versus salt water can determine whether a person floats or sinks. Has anybody ever seen this happen or actually noticed a difference anywhere? Unfortunately, I've never noticed because, see, fat floats. And so even in fresh water, I float very well. And so if you're floating, it doesn't matter whether you're floating in fresh water or salt water. Okay? And so I take people's word for it. Now, before we start here, to me, some people have always told me that I'm crazy, not just because of this slide, but to me, it looks like there's an optical illusion here that the gold one is bigger. Do you see that?
The
Yeah.
side looks smaller now.
Yeah, it looks smaller to me.
You say the gold one looks smaller?
I
Yeah.
think it looks bigger.
It's like that what color is the dress picture, right?
Yeah.
They're actually the same size, okay? So we're going to work on the assumption that they are the same size. And so this tells us the cube of gold has a greater mass than the cube of aluminum. Which cube has the greater density? Why?
Because the mass is greater than the density is greater.
Right. So our formula for density is mass over volume. And we said the volume is the same for both. So the only thing that changes is the mass. And the one with the larger mass is going to have the higher density. And so gold has the higher mass, so it has the higher density. Now, this is definitely not an optical illusion. The aluminum ball is larger than the gold one. It says they have the same mass, which has the greater density.
Still the gold is smaller.
It's still the gold. It's the same equation. What is the same here? The mass or the volume? The mass. So the M is the same for both the gold and the aluminum. The only thing that changes is the volume. And so if volume goes up, which way does density go? Down. And so the largest density will have the largest or the smallest volume? Smallest volume. As volume goes up, density goes down. As volume goes down, density goes up. So which one has the smallest volume? Gold. The gold has the smallest volume, same amount of mass, so it has the highest density. Here's another example. You can go home and try this, it works. Regular Coke sinks, Diet Coke floats.
Sugar and saccharin?
What about sugar and saccharin?
I don't know, I'm just guessing. That's why.
It's more dense.
Sugar,
than,
yeah.
What's more dense?
Well, sugar is when it's mixed in.
The Coke is more dense.
Regular Coke is more dense. But why?
Is it sugar?
What about the sugar?
It's more dense. It's like the salt, isn't it?
I just.
But
Oh, because you
how
have
is
to
it
put more
like-
sugar in there to sweeten it, less sweetener in there.
Yes. Aspartame in Diet Coke, general artificial sweeteners are very, very sweet. You don't need very much at all. If you look at the ingredients on Coke, second ingredient is probably corn syrup. The second ingredient is sugar. If you look at the ingredients on Diet Coke, the sort sweetener is all the way at the end. You don't need very much. And so the more solid that you dissolve in the water, the more dense it becomes. So you need a whole lot more sugar to taste as sweet as if you're using artificial sweetener. So if you have a cooler of melting ice and you want a regular Coke, you're going to have to reach down to the bottom. If you want a Diet Coke, it's floating right on top.
That actually makes sense.
If you want a regular Coke, but you don't want to get your hand wet, you're drinking Diet Coke. Okay. We said that solids generally have higher density than liquids. Does ice float or sink? It floats. Why?
Ice is
Crystalline
different, it expands.
Yeah. Over and over again this semester, we're going to see that water is the weirdest molecule around. It's basically the simplest molecule that we're going to deal with, but it is weird. Normally, we go from a gas to a liquid to a solid. And the density gets higher and higher as you go. But water forms a very complicated crystal. And when it forms this crystal, it actually has to expand in order to form that defined shape. A water crystal will always have this lattice shape. And built into the lattice is a lot of empty space. And so when that water freezes, it actually expands a little bit. So water is an exception. Liquid water is more dense than solid ice. The density of water actually will, as you cool it down towards freezing, you will get higher and higher and higher. 4 degrees Celsius, which is just above freezing, is the most dense temperature. As you go down from there, these crystals start to form and then it starts to come back out. So it comes in at 4 degrees and then it starts to come back out as it freezes.
So if you looked at it like with like an electron microscope,
Mhm.
did you see like little perforations? Or,
What kind of perforation?
well, like little holes.
Could you see
glass?
these?
Yeah, I guess.
You would need more than an electron microscope. You would need what they call it's an electron force microscope.
I think that sounds about
And so, in that case, you could probably say that. I don't think anyone has done it.
right. Oh, yeah. It seems cool though that it's like little holes.
Yeah. The other thing we measure is temperature. The temperature is just how hot or cold something is, but it's always relative to a standard number. Okay? Every temperature scale has a starting point, and then you measure up or down from that starting point. When we measure temperature with a thermometer, in science, we will always, always, always use Celsius and Kelvins. You will never, ever use Fahrenheit. If you're given Fahrenheit in a problem, you're going to have to convert it. So here are some conversions. These are on your cheat sheet, so you don't have to memorize them. These you probably will accidentally memorize because you'll use them so often. These you probably won't. And so you can convert between Celsius and Kelvin, Kelvin and Celsius, and you can convert between Fahrenheit and Celsius and Fahrenheit. There's no direct conversion between Kelvin and Fahrenheit, so you have to go through Celsius in between. In order to get Celsius, you take Kelvin minus 273.15. Calculate Kelvin, you take Celsius plus 273.15. So the difference in temperature between Celsius and Kelvin is 273.15. And that number is going to stick in your mind after a while. So if you want to go from Kelvin to Celsius, you subtract it. Go from Celsius to Kelvin, you add it. These are the 3 temperature scales lined up side by side. We have Fahrenheit, Celsius, and Kelvin. And so let's look at water boiling. Water boils at 212 Fahrenheit. In Celsius, it's 100 degrees Celsius, and in Kelvin, it's 373.15. Room temperature is about 77 Fahrenheit, 25 Celsius, 298 Kelvin, and the freezing point of water is 32, 0, and 273. Looking at these 3 scales, which one seems to have the easiest, at least the numbers that make the most sense? Why?
Intervals of 25.
Well, it's- freezing is 0, boiling is 100. It's nice, right? That is how the Celsius degree scale was defined. They said, this is freezing, we're going to call that 0. This is boiling, we're going to call that 100. And just make 100 little divisions between them, and then continue them up and down from there. This one is probably the second most obvious one. Can you see it? Where does this Kelvin scale come from? How did they define this scale? Just say it again.
It's still based on.
Yeah, it just has different starting and
But where did they had to pick those starting and end points though? Why did they pick what they picked?
Maybe like related.
It doesn't go below 0.
It doesn't go below 0. And so they said, well, why are we picking this weird number? Melt freezing point of water is 0. I mean, we don't say that this table is 0 meters long and then go negative and positive, right? We start from 0 and then we go up. And so that's Kelvin. The absolute lack of heat, no heat whatsoever, is absolute 0 at 0 Kelvin. And then it just goes up from there. So that's how that one was set up initially. And then we've got the American one, or the British one. Does that make any sense whatsoever? It actually made sense when they came up with it. What is body temperature? 98.6, okay? Now imagine you're a scientist hundreds of years ago measuring a bath. What do you think you're going to measure that as? 98.6. What nice number is 98.6 very close to? 100. So they measured body temperature, said body temperature is 100. That's what I'm basing everything off of. But then later on they realized, oops, it's not actually 100, it's 98.6. And so Fahrenheit does have some logical basis, but it was lost when they figured out they were wrong. Okay, moving on. When we take measurements, we can describe how good our measurements are. And we're going to describe them using precision and accuracy. In the real world, people use precision and accuracy interchangeably. Here, they are not interchangeable. They are very different things, okay? So, for the rest of your life, you're going to get annoyed when your friend uses the wrong term, okay? Because you're going to know the right way to use them. Precision is how repeatable your measurements are. If I measure the length of this table, I measure it 10 times, okay? I'm going to say that's probably, well, we'll call it 1.5 meters, okay? If I measure it 10 times and I get 1.4, 1.5, 1.45, 1.55, and they're all really close, that is precise. If I measure it to be 0.5, 8, 100, 0.2, those measurements aren't close together, right? That is not precise. Precise has absolutely nothing to do with how close you are to the actual number. So if I say this table is 0.1, 0.15, 0.1, 0.2, 0.158, all those measurements are very close together. That is still precise. I'm completely wrong, but I am still precise. Accuracy is how close you are to the actual number. And if you have a number of measurements, all you care about in terms of accuracy is the average. So we'll say I'm 2 meters tall, okay? If I measure myself twice, first time I measure myself 1 meter tall, second time I measure myself 3 meters tall. What's the average measurement? 2, which is perfect. And so even though I was nowhere even close on either of my measurements, my set of measurements is accurate. Okay? So don't forget that. For accuracy, if you have more than one measurement, you have to take the average of them. And so the example we just did were numbers. Okay? You can also think about this in terms of a dartboard. So looking at that picture, would you call that precise? Precise is always the easier of the two, especially with the dartboard. Those holes are nowhere near each other. You're all over the place. That is not precise. and this is where some people, it's very easy, other people struggle like heck to see this. But try to figure out where the average spot is there. Where would you say the average spot is? I'm going to start in the middle, and you tell me where to go from there. Which way?
Okay.
I'm going to go left. I'd say maybe a little bit down, but it's certainly left, right? There are more shots on the left than there are on the right. So the average is somewhere over here. And so that is not in the bullseye. So that is not accurate. What about this one? Is that precise?
Yes.
Yes. It's a very tight grouping, right? Is it accurate? No. Where is the average shot? It's right in the middle of that, kind of right there. You're nowhere near the middle. So that is precise, but not accurate. What about that one? Precise and accurate. Good grouping, very close together, and the average is right in the middle. So it's precise and accurate. And how about that one? Is it precise?
No.
No. Is it accurate? I would say the average is probably right about there, which is darn close to the middle. And so I would call that accurate, but not precise. Okay? You can probably see, especially with the accuracy, there's a little bit of fuzziness there. I mean, how close to the middle do you have to be accurate? Your definition may be different than mine. And so if you were looking at that and you wanted to make the case that the average was there and not there, and so that's not accurate, just tell me that you're saying it's off center, and so you're considering that not accurate. If you just tell me not accurate, I'm going to mark it wrong, because I'm going to assume you don't know the difference between that and that. Okay. More conversions. 12 grams to milligrams. How many milligrams are in a gram? 1,000 milligrams in a gram. What is larger, a gram or a milligram? A gram is larger. So when we go from a gram to milligrams, is my number going to get larger or smaller? Larger. Because we're going to need more of them. Milligrams are smaller, so I need more of them. It's like going from dollars to cents. If the price tag is $5, how many cents is it? 500. A cent is smaller, so when you go from dollar to cents, the number goes up. So if it's going to go, if milligram is smaller, my number is going to go up. Do I multiply or divide by 1,000? Multiply. So I would go 12.0 grams times 1,000 equals 12,000 milligrams. Okay. Now we got 12 grams to ounces. It says 1 ounce equals 28.34 grams. Again, using a little bit of logic, looking at that conversion factor we're given. What is larger, an ounce or a gram? An ounce is larger because it takes 28 grams added together, piled on top of each other, to equal 1 ounce.
Ounce is larger?
Ounce is larger because it takes more grams to equal 1 ounce.
If it was smaller, it'd be less than nothing.
Correct. So, if I'm going from grams to ounces, is my number going to go up? Is my number going to go down? It's going to go down. It's like going from cents to dollars. You're going from little to big. And so you don't need as many of them. And so am I going to multiply or divide by 28.34? I'm going to divide. So I have 12.0 grams times divided by 28.34 ounces equals what? 0.0234?
4234.
4234?
It goes there before. Just 4, 2,
4234. Got it? Yay. Unit, what's the unit here?
Ounces,
Per ounce.
grams per ounce.
Just ounces. I think
Yeah, make it a density.
you're trying to follow this,
Yeah.
and that is going to sort itself out when we start doing the conversion.
I'm just
factor.
mixing up the density, you know.
Are we not dividing, I mean, when we were dividing density, we took both units in
So,
consideration.
by doing it this way, I am skipping part of the math, and that the units here will really sort itself out. Maybe next slide? No. In a few slides. Don't worry about the fact that we're going to divide by ounces. We'll sort that out. And so, the correct answer here is 0.423, not 0.4234. So that gets back to what you were talking about, the rounding. So why is it 0.423 and not 0.4234?
36 eggs.
Sig figs. Yes.
Since it's, the biggest number is 28.34, all the 0.423, all of it's 4 sig figs.
Right track. This is actually, we'll talk about the rules. 0.423 is actually 3 sig figs, and you don't use conversion factors in determining sig figs. So, it is definitely sig figs. That is the correct answer. That is wrong, you get a stamp. That is wrong, you get a stamp. When you get a stamp, you lose points.
So how do you get it to the right one, 0.423?
Thank you for asking. Sig figs. You have to figure out how many sig figs your answer needs to have. You are going to hate sig figs. Okay? You are absolutely going to hate sig figs. Sig figs are horrible. Okay? They are the bane of every scientist's existence. Okay? Sitting in here, we're all going to make a pact. If we ever become the king or queen of chemistry, we're going to get rid of sig figs. Okay? I am an adjunct. I don't have that power. Okay? You're a student. You don't have that power. Maybe one day. Okay? Pinky swear. We'll get rid of it. You will save generations of people lots of headaches. But we have to deal with the headaches. Because we can't get rid of them. So sig fig stands for significant figures. We have some rules. When we look at a number, figure out how many sig figs it has. So we can look at that number, figure out how many sig figs it has. We can look at that number, how many sig figs does it have? We have to go through these rules. Any number, any digit that is not a 0 is significant. So 4234 is automatically significant. That 1 and that 2 are automatically significant. That's the easy part. The hard part is figuring out which zeros are significant and which ones are not. If you have a 0 that's between two non-zeros, like that 0 and that 0, those zeros are significant. Zeros, what we call leading zeros, the zeros at the beginning of our number, are never, ever significant. Trailing zeros, zeros at the end of our number, they are significant if there is a decimal place anywhere in the number? Is there a decimal place in that number? No. Mathematically, it's right there, but it's not written. And whether it's written or not is what matters. There is no decimal point in there. There's no decimal point in that number, so those zeros are not significant. If I erase this, and I make it 0.0, now we have trailing zeros, and we have a decimal point. So they are all significant. So how many sig figs are in that number? 1, 2, the easy ones. These are significant. 3, 4, 5, 6. There are 6 sig figs in that number. How many sig figs are in that number? 4. These got 4 easy ones. That's a leading zero. Is never significant. How about that number? How many sig figs? 1. It's got the 1. There's no decimal point, so the trailing zeros are not significant. What about that number? 3. 1, 2, that's a trailing zero with a decimal point. So we have 1, 2, 3. How many in that number? 4. That's easy. Okay. So the first problem is figuring out how many sig figs each number has. Then, what do you do with it? How many sig figs? 2. How many in that one? 1, 2, 3, 4, 5. These are significant. 6, 7. How many in that one?
6.
I have 4 and 6. There's obviously 4.
Didn't you say when there's a leading zero, they are not?
Yeah, but that's for trailing, not leading.
Leading zeros are never significant, whether there's a decimal point or not.
Okay, so that's not significant.
These zeros are not significant. And so we have,
Oh, so we consider, okay, I
If
get
they
it
come
now.
before, they're not. If they come after and there's a decimal, they are.
Okay, I thought the leading zero, you just mean the zero before the decimal, so
no,
it counts the zeros even after the decimal.
It's before the first non-zero.
Okay,
Does that make sense?
yeah.
Okay. We're going to talk more about scientific notation later today, but if you're doing sig figs in scientific notation, you can completely ignore this part. You just look at that part. So how many sig figs are there?
1.
What? How many in this one? We have 1, 2, 3, 4, 5, 6, 7, 8. Right? Okay. So, when we're doing a math problem, though, we don't just write a number and figure out how many sig figs it has. We do math with them. And so we have to take those sig figs, we plug them in, and then we figure out how many sig figs our answer has, which is what really led us to this question. Why is this not the correct answer? And so if it's multiplication and division, this is the easy one. Multiplication and division is easy. You look at all of the numbers that went into it, figure out which one had the least number of sig figs, and that's how many your answer has. So how many sig figs does that have? 3. How many does that have? 4. So how many should your answer have? 3. And so your answer has 3, and so we need to round, right? We have 1, 2, 3. We're going to round there. We're going to round there. And you round using the same rules that you've always learned, right? 0, 1, 2, 3, 4 are going to round down. 5, 6, 7, 8, 9 are going to round up. And so that's why this correct answer is 0.423 ounces, not 4234. So here's some examples. You got 2.06 times 4.3. You put that in your calculator, and here's going to tell you 8.853. Is that the correct answer in this class? No. How many sig figs should your answer have? 2. That has 3 sig figs, that has 2, so your answer has 2. So what is the correct answer? 8.9. I'm going to round that 5 up to 8.9. Put that in your calculator, and what are you going to get?
Oh, divide.
You're going to get 2. 6 divided by 3 is 2. What is the correct answer in this class? 2.0. And so, in math, the answer is 2. But that only has 1 sig fig. We have to have 2 sig figs. The 6.0 is the lowest number, and that has 2. And so I can't change the meaning of this number. I can't change it to 2.1. The 2.1 is not 2. I need 2 with 2 sig figs. And that's 2.0.
Do you have a nail in that marker?
If you put that in your calculator, you're going to get something really long, right? Somebody do it. What do you get?
Which is 4.1234 and so on.
That's 4.4938,
Alright.
37,156.
4.4938
271.
271
56.
56. Is that the correct answer?
Yeah.
No. What is the correct answer? 4. 4 times something other than 1 equals 4. So it's like nothing happened. What's the answer here? What's 5 times 2? 10. How many sig figs do you need? 2. So I've got 10.
So you have to put it, yeah.
But you can't put a decimal because on the second zero count.
Yeah, but the zero after
Oh, yeah.
one doesn't
It's
count.
just the zero.
Yeah, it's just
trailing.
10.
Just put
How many sig figs does that have?
2, 1.
1.
Just put a decimal after.
How many sig figs does that have?
3.
3. I added 1 0, and I went from 1 to 3. How on earth can I get 2?
Round it up.
You can write that.
Oh.
10 points.
So imaginary factors.
That is the only correct answer. 10 without that decimal is wrong. 10.0 is wrong. 10 point is correct.
What's the point of this?
Decimal. Decimal is the point.
That's an imaginary.
Huh? That's funny. Fun.
That's why they pay me the not so big bucks. So multiplication and division is the easy one. Addition and subtraction is the hard one. Okay? I am going to hold you to these rules on questions about sig figs. So if there's a question that the question itself is about calculating sig figs, you have to use these rules. Later in the semester, when our math problems get big, and there's addition, subtraction, and a multiplication in the same problem, I would suggest, I'm not going to hold you to this, okay? Just pick the smallest number within the multiplication and division rules and run with it, okay? But we have to learn the addition and subtraction. And to do the addition and subtraction, you actually have to do it longhand like you learned in the first grade. You can't just put it into your calculator, figure out how many sig figs you need to round to, and do it. Because in order to do it, you have to line up the decimal places, write it all out, and then draw this line. So, we have 243.506 plus 0.12 plus 4455.9. We've got 3 numbers. We're going to line up the decimal points and let numbers fall where they're going to fall. Once we line them up, we find the number that has the leftmost last digit. So find the number that ends the soonest when you're going from left to right. In this case, it's this one. That one ends the soonest. And so we draw a line right there. Then we do our math, our addition, just like we would do in first grade. And now we have our line to round over. And so that 2.6, is that going to round down or up? It's going to round down. So the correct answer is 4690.5. So you have to write it out. Don't try to do that in your head, because you're probably not going to line it up correctly.
So anything to the right of the line is not sig fig?
Correct. So you draw the line, and anything to the right is not a sig fig. So it's weird, because in multiplication and division, we're going off how many sig figs the numbers we plugged in started with. In addition and subtraction, it's really based off how many decimal points they started with. The number of decimal points determines the number of sig figs in our answer. So line it up, draw your line, and round. So here we've got 587, boy, I made this hard on myself. 362708, 2708. I've got 4.36. I'm going to line up the decimal point. So I have 4.36, and then I have, wow, 2798, 2798, 329, 329, 829. That's a plus, that's a minus. I would suggest not trying to do that math with longhand, because you're going to end up doing it in two parts, right? So what you can do is plug that into your calculator and then line up the decimal point of your answer with your decimal points here, right? So somebody do me a favor, put that into your calculator.
789.
Where?
The very end, does that say 798?
Oh, thank you.
Okay.
So once you got it, I'm going to put a decimal point here. Somebody read me the numbers going to the right of the decimal.
What's that?
To the right of the decimal.
Start with decimal and go to the right.
Double 562.
562.
556.
Okay. Now, start with decimal
Double
and
five.
go
That's
left.
2 5.
There's 2 5s.
5562. Now start with decimal.
133.
133.
829 negative.
Okay. So now we line up the decimal point of our answer with the decimal point of our starting numbers. Now we have to draw our line to round. Where is it going to go?
The
Answer
4
that
is
first.
small.
This number ends here. This one ends there, that one ends way out here. So I'm going to draw my line there. And so I get negative 92833.56. 6. Maybe this one over. Does this make sense?
No.
Well, what? What about it?
The rounding, like, do we count the numbers after the line?
Well, you're gonna round, does 6 round up or does 6 round down?
It rounds up, but then when we do that line, it kind of confused me. Do we stay on this side of the line, or we can run the numbers that are on this side of the line?
What we do at the line is we keep everything on the left,
Okay,
and then we have to round everything on the right in order to get rid of it.
okay,
So in the end, we can't have anything on the right of the line.
The right's only for rounding.
And so this 6-2 rounded that 5 up to a 6.
right, okay.
Yes.
Why the line in the first column was after the
So what you need to do is you need to look at all of your numbers and figure out, when you're going from left to right, which one ends the soonest. And so we're going along, this one hasn't even started yet, but we're going along, and this one runs out there. These keep going, but this one stops. So when the first one stops, you draw your line. Make sense? Any other questions? We'll take our break now, and we'll start at 29 after, 10 minutes from now. So,
You want one?
what we normally do
You want one?
in this lecture, or this, and we'll go over Canvas questions. That's the reason for this intro videos.
It's gonna be easy.
You know, the lecture, if you have questions, obviously we go over in class after. If you have questions during the week, if you still don't, you get it wrong, you still don't know.
For, since those are gonna be like, some of those or all of them are gonna be on the quiz, it was just the name and the symbol, right?
Correct.
At least for now.
For now, but afterwards you'll have a periodic table that actually has.
Yeah, has everything.
There's only 3 questions, right?
3 multiple choice and then that stuff.
All of it?
All of it?
No, no.
Laura's gonna
No, it's okay.
pick some stuff.
I picked randomly picked some.
Right, so you're like, no, right?
You
No.
might want to pick the one that's not so easy.
Using reverse psychology.
I would.
If you're running like this, everybody's gonna want to stay in class and not go home. Yeah, 'cause then you gotta go outside.
I have to roll up. Right.
It's not still raining.
Yeah.
Yes, it is.
Supposed to rain till about 9 o'clock, so that was a radar thing too. Is that today? Watching this week?
Yes, but it's Weather Channel. It's as dramatic as possible. Weather Channel also turned up their sensitivity on the radar a couple months ago. And so what is now red used to be yellow. But red instills fear.
It does.
If you're afraid of the weather, you watch the Weather Channel. So they make it as red as possible to make you scared.
And half hour on my spring. picture or the current? Can you do the future one? Yeah. The future. Make it
Midnight. And the next day, and the next day, and the next day. If you, I don't know if you check it throughout the day, they can really change throughout the day. You can wake up and it's an 80% chance of rain. I get to work, it's a 10% chance of rain. An hour later, you hear thunder and it says 90% chance of rain. And then it's raining and it says 0% chance of rain.
Yeah, it's at the end.
Seriously, I mean, how awesome is it to get paid a
So it's not
salary
based on like
to
the
be
likelihood
wrong
of
50%
the
of the
rain,
time?
it's based on like the amount of the air that will hit the rain.
When you work it out the statistics, it actually comes out the same.
It does.
And so it's supposed to cover a certain area around.
Yeah.
And so if it's imagined to Alachua County,
Right.
and it says 50% chance of rain, that means 50% of Alachua County should get
Right.
rain. But if you work on it on an individual person's level, that also means there's a 50% chance that you will get rain.
Yeah.
I love that.
Yeah, and property looking for like, so like if I know there, like, it would be a boring, there will be like sunshine. Yeah. That's just Florida. Where are your lectures posted? They're on,
You could find the slides.
No.
Oh, the actual video.
Yeah.
If you go to the home page of the Canvas page, the front page, there's a link right there, and there's a checklist there. It's in the chart.
How come when you post the slide on the open campus, it doesn't? Thank you.
show up.
Why they don't look like that?
Right, because like if it's like that, I can print it a certain way, but when you have it up, it doesn't open up to that file.
It's a PDF.
Yeah, they're like a
PDF.
Yeah, like
You can
when
print a
there's,
PDF.
when there's an answer that you can't see it online.
How you delete most of the answers.
Why do you do that?
So then you have to write
my
them.
program on my computer and I can't open it on the PowerPoint.
You open it as a PDF. You need to open it in Adobe Acrobat. It's a free program.
Right, but only thing is that, in that program, you can't select the app, but they can four slides on one page.
When you go to print, it'll.
You post that slide thing to the canvas?
So if I go File, Print, I need to hit Multiple. And now I can do 6 per page, 9 per page, or 1 by 3, however you want. Is that,
I'm checking, mine doesn't look like that when I look at it.
it's probably, it's there somewhere, you're going to have to play around with it.
Yeah, you might have to hit properties and then look like computer you want.
When I post those, I take all the colored background out, say ink, and then I go through and change all of the non-black text that I can change. I change to black, so you're not printing yellow on white, which you can't see. But there are some, particularly numbers in there, that they're images, not text, and so I can't change the color. And so those I either delete, so that you have to write them, or I leave them, so if you can see them, you can see them. If you can't, you can't. Anybody has family in the northern part of the country? Did it snow there? My parents are in Michigan, and it snowed on May 15th.
It's snowing like right now for me.
Is it?
Yeah. My sister's in New York and it's not snowing.
Is it snowing there? My daughter's up there.
I don't remember it ever snowing this late in May.
No, it's
It
cold.
snowed on Mother's Day a few years ago.
Yeah, my birthday is in the middle of April, and it would occasionally be cold and a little bit snowy then. When's your birthday? 22nd?
Oh, mine's 21st.
There's a lot of birthdays that week.
When's your birthday? April, 3rd.
There's the 19th, 20th, 21st, 22nd, 23rd. A lot of birthdays.
I lived in Colorado, it was always, it would snow like in the summer even sometimes.
Were you up in the mountains?
Well, I was in Colorado Springs, so it's higher than Denver. So in the mountains, yeah, they pretty much always had snow.
No, thank you. So we're going to move on to scientific notation. And so scientific notation is what we saw in that table a few slides ago with a number and then times 10 to another number. What this allows us to do is to take a number with a bunch of zeros in it and condense it down into a much more manageable number. So in scientific notation, we have a number, we're going to call that C, and that number is 1 to 10.
It's only to 9.
Say it again?
Can it only be to 9? Since you don't
Well,
have-
it's between 1 and 10, but it can't be 10. So it's at least 1, but less than 10. Okay? And so you got that number times 10 to the n. And n is an exponent, and it's a positive or negative integer. Now, what do we mean by an integer? It's a whole number. So you can't have times 10 to the 1.1. You can have times 10 to the negative 0.5. You can have 10 to the 0, 1, 2, 3, negative 1, negative 2, negative 3. Those are whole numbers. So you have a number times 10 to an integer. And to get C, you're going to move the decimal point to the right of the first non-zero digit. So if I have, oh, come on.
Is that a brand new box of markers?
No, I think there's another box in here. Hopefully there is, or I'm going dumpster diving. $834. We need to put the decimal point to the right of the first non-zero. Where is that? After the 8. So I'm going to put the decimal point there. That is my C, 8.34. Then we have times 10 to the something. To get n, you're going to count how many decimal places you had to move the decimal. Okay? And so we started with 834. In math, the decimal point is there, we just don't write it. Correct? It moved it from here to here. So we moved it 1, 2 places. Count them, okay? We moved it 1, 2. If you move it to the left, the n is a positive number. If I have 0.0834, I need to move my decimal point to the right of the first non-zero. Where is that?
Behind
The 8, go from left to right. find the first non-zero, it's 8, put decimal point there. So it's still 8.34. That is still my C, 8.34. And I moved that decimal point 1, 2, so it's times 10 to the 2, but I moved it to the right. When I move it to the right, it's negative. So here are some examples. You've got 3,245. What is my C? What's my number? 3.245 times 10 to the third. 1, 2, 3, and you moved it to the left. Okay? It is 3. So I see people, you're not the only one, taking your pen and doing this. Okay? Do that. If it's up here, do it. If it's on your paper, use your pen and do that. Okay? If you try to look, especially when you get to these bigger numbers, if you try to eyeball that, you're going to get one wrong. Right? So you may feel stupid doing it, but you're not stupid. Okay? If Albert Einstein was sitting back there, he would be going like this. Okay? We all do it because you don't want to get it wrong. To me, not doing it is stupid because then you're going to get an answer wrong. For what? Your pride? Forget your pride. Get it right. And so we've got 3.245 times 10 to the third. What about the next one? What's my C?
The same.
It's the same. 3.245 times 10 to the
Negative
1, 2, 3, 4, 5, 6. Negative 6. What about the next one?
Same.
3.245 times 10 to the 9. Are you doing this or are the answers on the side?
No, I got it before.
So we moved it to the left 9. If you counted them, it's 9, so we get times 10 to the 9. What about this one?
5.0607.
5.0607 times 10 to the negative third. 1, 2, 3. What about the next one? 8.8.
Just
10 to the 1, or you can just leave the 1 off. Right? What about the last one? 2.45. What if I tell you, and this is not going to be on the quiz, it has to be in scientific notation. You have to have times 10 to the something. 0. Anything to the 0 power is 1. And so 2.45 times 1 is 2.45.
Did we not move the decimal 2 times? But was it not
It was already like that.
2.45? Or it was only?
It started as 2.45. And so another way to figure out 0, you moved it 0 places.
But it
So-
would never go over 9, never go over 10, or between 1 and 10, or something like that, you said it would never
Correct.
go over that?
Because if it's over 10, let's say it's 10.1, that decimal point is not to the right of the first non-zero. It should be over there. Does that make sense?
Okay, can we move, like literally move it with your hands? The box 3. Like I want to see how we did that.
So it started here,
Okay.
okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. Getting back to, does it make sense?
The little number can't go over.
Right, so we have C times 10 to the n. That C cannot be over 10.
Okay.
10.1 is over 10.
She's talking about the exponent of that.
You're talking about this number?
Yeah.
Oh, that number can be anything you want it to be. As long as it's a whole number, it can be 5 billion. It's a lot of zeros. You can put scientific notation in the scientific notation if you wanted to. You're going to have to put these scientific notation numbers into your calculator. Everybody has different calculators. So how you put it into your calculator might be different than how your neighbor puts it into their calculator. So it's up to you to learn how to put it into your calculator. That may mean asking your neighbor to help you. That may mean asking me to help you. But I don't know what calculator you have. So I can't tell you, by standing up here, what you need to do. The easiest way, well, maybe not the easiest, the simplest way, is to actually just put the whole thing in parentheses. Let's say you've got 3.8 times 10 to the third, something like that, okay? Put it in parentheses. If you do 3.8 times 10 to the third and you don't put that in parentheses, you're going to get all kinds of order of operation errors. There's a lab, maybe the 5th week or so of semester, that you're going to be doing a lot of this. And half of you are going to get the wrong answer over and over and over again, and it's because you're not going to put these in parentheses. Okay? So that is the simplest way to do it. The way I do it, and the way if you get comfortable doing it, and that I suggest, is on your calculator. There is probably a button that is, it looks like two capital E's next to each other. It may be a button you have to hit second and then a number. Okay? It's weird because the button says EE, but when you hit it, on the screen it only shows one E. I don't know why. It seems dumb to me. But you're going to hit that, and then you hit 3. That EE or that E means times 10 to the. So that's 3.8 times 10 to the third. And when you do that, it automatically ties that together in terms of order of operation. So it knows that that is a thing. And I can't break it up. I can't take that 3.8 there and 10 to the third over there. Okay? If you're going to use the E, make sure you're using the capital E. There's also a lowercase e. Lowercase e is entirely different. That has to do with natural laws, which is not what we're doing. So make sure you're using the EE or the one capital E. I guess some calculators may say EXP instead of the EE. I think you're all comfortable with this. Does anybody want to do some examples? Is there one up there that really jumps out at you? Let's do the first one. This first one's a nice example. What's my C value? 9.0000650 times 10 to the 9. So when we started talking about scientific notation, what did we say was the purpose for it? To make a number smaller. Did we make that any smaller? No. I actually made it bigger. Because I had to write the same exact number of digits times 10 to the 9th. I made more work for myself. So scientific notation is only useful when you have non-significant zeros at the beginning or the end. When you take a number and you put it in scientific notation, you can't change the number of sig figs. When this number, those zeros are significant. So I can't get rid of them. In this example, those zeros are not significant because the decimal point is not there. So I can get rid of them. So in that case, it does save me some writing.
specify in the test whether or not to do it?
So, if you have a question that is specifically asking you for scientific notation, then you have to do it. If a question does not tell you the answer needs to be in scientific notation, it's up to you whether you put it or not. And so that would be correct, or that would be correct, or that, or that, or that, or that. If I don't specify, I lost my ability to choose which way to wrong. Yeah.
If you can get rid of all the numbers on zeros
And which one? This one?
on that second to the last one at the
That
bottom,
one. Okay.
then why didn't you do that on the end?
Oh, yeah. You left.
Because I didn't notice that the slides were wrong when I copied them. That's why. But you
So
noticed.
originally, that should have been just 2.998.
Yes. In order for this to be true, it would have had to have been a decimal point. Okay, two things change when I go home. I don't know how these are made 5 semesters later. You must be paying attention better than everybody else, including me. So, go ahead, question?
I was gonna ask about that, these numbers. When, can we use a calculator? Because when I do it on the calculator, it gives me an exponent of a -12. Am I doing it wrong? Second.
If you go 0.00000834, and then hit it, it tells you it's 8.34 times 26. You either have to put in the whole number without an E,
Okay.
or you have to put the 8.34 with the E.
Okay, thank you.
So we can do math with the scientific notation. So we can take that number and multiply it by that. Okay? And this is easier than it looks. You just break it up into 2 parts. You take the C's, these numbers, the coefficients, what we call them, the coefficients, and you multiply those together. 4 times 1.5, 4 times 1.5, and then you put times 10 to the, and then if you're multiplying exponents, you add them together. So this is 6 plus -3. And so we get 4 times 1.5 is 6.0, with the correct number of sig figs, and then 6 plus -3 is 3. And so that answer is 6.0 times 10 to the third. If you're dividing, it's the same idea. You're going to take the coefficients, divide that one by that one. What's 4.0 divided by 2.0? 2. The correct number of sig figs is 2.0. We have 2.0 times 10 to the, and here when you divide, you take the first one and you subtract the second. So we have -2 minus 3 is what? -5. -2 minus 3 is -5. If you raise scientific notation to another exponent, you're going to take that exponent and you're going to put it on both of the parts inside the parentheses. So you're going to take 3.0 to the second power, so you get 3.0 squared, which is what? 9. 3 times 3 times, 3 times 3 is 9. 3 squared is 9. Now we've got 10 to the 4th to the second. If you have an exponent to an exponent, you just multiply it. So it becomes 10 to the 4 times 2. 4 times 2 is 8, so it's 9.0 times 10 to the 8. I've got some examples. How would you do this? What's the first thing you would do? First thing you would do, 6.78 times 5.55, what is that? Say it again? 37.629. What are you going to do with the exponents?
And
You're going to add them together. And so 3 plus negative 4 is 10 to the negative 1. So we've got 37.629 times 10 to the negative 1. Is that our correct answer? Why not? Correct. That decimal place has to be here. So we're going to move it 3.7629, but then what do we have to do? We're going to have to change our exponent. And so we moved it to the left 1. So what do you think we do to that? You're going to add 1, right? Because if you go to the left, you add an exponent. So we get negative 1 plus 1 is 0. So you've got 3.7629. Now we've got the second one. What's the first step on the second one then? Got 2.99 divided by 4.03. What does that equal? 0.7419. I just realized we didn't do sig figure over there. We'll come back to it. 0.7419. What about our exponent?
negative 15.
How do we do this math?
Subtract it, not interested.
You got negative 9 minus negative 6.
Plus negative 15.
Negative 9 times 6.
With division, we take the first one and we subtract the second. So what is negative 9 minus negative 6? Negative 3.
Negative 3?
Negative 3. So you've got negative 9 minus negative 6. That double negative becomes negative 9 plus 6 equals 3. Negative.
Oh, okay.
Thank you. And so we end up with times 10 to the negative third. Is that the correct answer? No, why not?
Negative.
You need to move it over 1. We get 7.419 times 10 to the negative 4. You moved it one more to the right, so we go down 1. Is that the correct answer? No. Why not? Sig figs. How many sig figs should our answer have? 3. 2.99 has how many? 3. 4.03 has how many? 3. So our answer should have how many? 3. What is that number with 3 sig figs? 7.42 times 10 to the negative 4.
I'm a little lost. I mean, what determines us moving the decimal? I thought what determines the decimal, how many it moves, it's the exponent that we have. Like if we have a negative 3 exponent, we'll move to the left 3 times.
What we're doing here, we're not undoing this. We're correcting this problem because in scientific notation, the decimal point has to be to the right of the first non-zero.
Okay, like right here, I thought that negative
This one?
1, that's what made us move to the,
No.
it's not there.
This isn't what's making this move. We have to move this, and when we move that, we have to change that. So
Okay,
this drives that.
okay. I'm a little lost, but I'm seeing it a little bit. Like this moving of the decimal, that's where I have confusion. I see everything except when we start to move the decimal to the left or to the right.
Okay. Did you understand it when we were doing, we had the big table, and we just had numbers, and we were putting them in the scientific notation. Was the moving decimal point there? Okay.
Yeah, you mean the ones in the little box?
Yes.
Yeah,
And so it's this moving that's confusing to you?
yeah.
Okay.
I think all the moving's confusing. Like, I feel like I'm getting it, and then I'm not getting it.
Okay. In order to understand this part of the moving, you're going to have to understand the first part of the moving. So my suggestion would be, if you want the essay after class, we can talk about it. If you want to go home and look at your notes, email me, whatever you think will work best.
Okay.
So we're going to come back to here. I said this was wrong. What's wrong about it? Sig figs. How many sig figs should we have? 3. So it should be 3.76 times 10 to the 0. And then the last one, 7 times 10 to the 3rd to the 4th. How do you do that? You've got 7 to the 4th times 10 to the 3rd to the 4th. What is 7 to the 4th? 2,401 times 10 to the 12. Exponent to an exponent, multiply. Got 10 to the 12. Is that the correct answer? No. What do you have to do? Set aside a decimal place. So it is here. We're going to go 1, 2, 3. If we move it 3, we end up with 2.401 times 10 to the what? 15. You started with 12. Then we moved it 3 more to the left. Every one you move it to the left, this number has to go up by 1. We moved it to the left 3, so it went up by 3. Is that the correct answer? No. Sig figs. It should be 1 sig fig.
Are you supposed to do sig figs twice then? When you first multiply or divide the original, the first set of numbers, you're supposed to,
My suggestion is to wait to the end. Sig
Okay.
figs. I would just work it all the way through, get to your final number, say how many sig figs should my answer have, and do it.
Okay, so what if like number 2, what if it was like 2.999 and then 4.03? What you supposed to do the line thingy after you done?
Multiplication and division is the simpler one. You just take the smaller of the two. So in your case, this one would have 4. This one would have 3. So your answer would have 3.
Okay.
And so here, how many sig figs do we start with? 1. So our answer needs to have 1. So it's just 2 times 10 to the 15. Okay. Now we're going to get back to our conversions. And we're going to do it the conversion factor way. My suggestion is to get very comfortable doing it this way. Okay? A lot of the ones we did before were really easy conversions. It's just a matter of, do I need to multiply or divide type of a thing. But we're going to get into much more complicated things. And we're going to get into conversions that are multi-step. Okay? Sometimes 3, 4, 5 steps. Okay? If you do it the logic way, the more times you do logic, the more likely you are to be illogical and get it wrong. But also, it gets harder, and you're trying to keep track of all that stuff in your mind, right? But if you do it the conversion factor way, you write it out as you go, and then when you get to the end, you have written out what you need to put into your calculator. Okay? And so there are 2 ways to write this. There's the way that the slides are made up, and then there's the way that I learned and that I prefer. So I'm going to do it my way, and then for the rest of the semester, a lot of the answer keys, I didn't change. I left them in the other way. That way, depending on which way you prefer, you have an example that answers it in both ways. So if you like my way, it'll be up here. If you like their way, it'll be on the slide. Okay? So dimensional analysis is a way that we do conversions that is based on units. You plug in the units the way they want to go, and you'll see what I mean by that, and the numbers will follow. It's what I consider idiot-proof conversions. The units literally tell you what to do. You can do a 5-step conversion and not have a clue what you just did and get the correct answer. Okay? So let's see how that works. The first thing you got to do when you're doing a dimensional analysis problem is think about where you're starting in your conversion. There's always a starting point. And then you also have to figure out, what am I trying to end with? If I'm going from miles to centimeters, I'm starting with miles, I'm ending at centimeters. But I can't go straight from miles to centimeters. So I'm going to have to do a bunch of steps in between. And so I'm starting at miles, I'm going to centimeters. I may know relationships, I may know how many feet are in a mile, how many inches are in a foot, and how many centimeters are an inch. Those are relationships that I know and that I can use. Then you're going to set up your problem, and then at the end, do a little quality check, a little discount double check, right? Does it make sense? If you're going from miles to centimeters, should your number go up or should it go down? It should go up. If you get an answer that's smaller than what you started, something's wrong. If you get a number that went up, you still don't know that it's right. Because maybe it's 5 and you have 8,000. But you know at least you went the right direction. There's no good way to quality check yourself past looking at did it go the right direction. So my way is this grid method. Has anyone used the grid before? Okay, a couple of them. And so we're going to do one easy conversion to start with. We're going to convert 2 inches to centimeters. When you're doing the grid, you find out where you're starting. And we're going to start at 2 inches. And where you're starting always goes in the top left corner. You're going to write what you're starting with, and you're going to draw your first part of the grid. You're going to draw a little cross shape like that. Whatever unit is here, no matter what it is, it has to go there. Always. The unit that's there will go there. And then what we write here is a conversion factor. When you write one thing on top of another, they have to be equal to each other. Because in math, you can always multiply by 1, right? Multiplying by 1 does nothing. It doesn't change anything. And so if you have a fraction that's the same on the top and the bottom, that fraction is 1. And so mathematically, if these two things are equal to each other, you didn't change anything. You didn't change the number, you changed the unit. And so this is a conversion factor. We're giving the conversion factor 1 inch equals 2.54 centimeters. And so we take that conversion factor and we plug it in. It says 1 inch, so I'm going to put 1 inch equals 2.54 centimeters. And when you write this, the unit that's in the top right corner is the unit that you're going to end with. And so what unit are we trying to get to in the end? We're trying to get to centimeters. In here, in my calculation, I have centimeters in the top right corner. So that means in my conversion, I have started at inches and I have ended in centimeters. So I've written it all out. I now just have to do the math. And to do the math, you take everything on the top and you multiply them together. So I get 2 times 2.54, which is equal to what? 5 point.
Just 1.
5 point.
Just 5.
Okay. Oh wait. Thank
Oh
you.
wait, no, just 5.
We're not dealing with Sig Figs yet. Wait till,
2 times 2.54,
yes.
That's right.
okay.
So we multiplied everything on top, and we got 5.08. Then we have this horizontal line here. Write the horizontal line, multiply everything on the bottom, and put it here. We got nothing times 1 to 1. Now you do that math. What's 5.08 divided by 1? 5.08. Now get your unit. The unit in the top right corner is centimeters. Put centimeters. Is that the correct answer? Yeah.
I was gonna ask a question. I did it a little differently. I multiplied 2 times 1 and then divided it by 2.54 and I got the same answer. Would that always work or?
I don't think that did work. So you,
Well, us multiply.
Yeah.
can I see what you
Yeah. I didn't really know it at all, but I multiplied 2 by 1 and divided it.
What is it? 5.08.
Divided 2 by.
2 divided by 2.54 is 5. I would, if you can figure out how to make your method work, that's fine. But I would really try to use this way. We're going to use this not just for measurement conversions, but also really chemical reactions and bigger, more complicated things later on. Is this the correct answer? No, why not? Sig figs. How many sig figs should I have? 1. I started with 2 inches, and so I need 5 centimeters.
So this 6 big thing apply to everything.
Everything. Next time you're at Publix and they ring up your check, you can tell the checker, my bill is in the wrong number of sig figs. Just see if they'll see what they'll do.
There's a lot of medical students in grade school, so maybe.
Don't get me started. Med students are probably the worst people to ask questions. Don't get me started on med students. Any pre-meds in here? 1. Sorry. And so remember, in the grid, you start top left, you end in the top right. Things are on top of each other are conversion factors. They're equal. And whatever unit is here goes there. If we were going to take this another step, centimeters would go here. If we wanted to take this and convert it to millimeters or meters, we could go inches to centimeters to millimeters. We go centimeters, centimeters, and then the conversion factor between centimeters and meters. So here is a more complicated example. We're looking for how many inches are in 2 kilometers. You can't do that in one step. If you were at home and you could look up the conversion factor, Google knows the conversion factor between inches and kilometers. Google actually doesn't even make you know the conversion factor because you could just type in how many inches are in 2 kilometers and it's going to tell you. But that's not going to teach you anything. And you don't have Google right here because you're not supposed to be on your phone, right? So we have to do it longhand. What are we starting with? 2 kilometers. We're starting with 2 kilometers. That is in the top left corner. What unit are we trying to get to? In the end, in the very end. Inches. So we're going to have to go step by step by step, and we're going to know that we're done when we have inches in the top right corner. Okay? So I've got 2 kilometers. I'm going to draw my first box. What unit has to go here?
Kilometers.
Kilometers. That unit has to go here. Based on the conversion factors we have, and what one can we use here?
1,000.
1,000 meters equals 1 kilometer. So I'm gonna say 1 kilometer equals 1,000 meters. Do I have the right unit in the top right corner? No. So I have to go further. I'm gonna draw another box. What unit has to be here? Meters. Always take that one, and copy it down here.
Oh, we keep doing that?
Over and over and over again, yes.
Okay.
So you can
That unit will always go here, yeah, so it cancels. And so kilometers and kilometers are going to cancel, meters and meters are going to cancel, and in the end, you're just gonna have one left up here. So of the relationships we have there, which one can we use now? We have 1 meter equals 100 centimeters. Do I have the right unit in the top right corner? No. So I have to go at least one more step. So what unit goes here? Centimeters. That is copied down here. Now what conversion factor do I use?
2.54.
We have 2.54 centimeters equals 1 inch. Do I have the right unit in the top right corner?
Yes.
Yes. So I'm done writing it out. Now I have to do the math. So I have 2 times 1,000 is 2,000 times 100 is 200,000. On the bottom, I have 1 times 2.54 equals 2.54. What is 200,000 divided by 2.54?
78,740.
78,740?
You want the decimal?
Sure.
0.15.
0.15. What is my unit? Inches. And there's your first example of me writing something long. It goes down. I don't know why. But, so we've got this answer. Is that the correct answer? No. Why? Sig figs. Yes. How many sig figs should I have? 1. So what is my answer? 80,000 inches. That has 1 sig fig. The 8 zeros are not significant.
I hate this 6 feet.
Me too.
Oh my
So if you
goodness.
put a decimal at the end of 80,000, does that make all those zeros significant?
Yes.
Okay.
Can you just tell me right on this one before I'm like completely gone lost? How do we do 6? Yeah, that way. There on this problem.
Yes?
Yes.
And so we did the math, right? We completely ignored sig figs.
Like I always can get to the other part, but whenever we have to take it to sig figs, whatever it is.
So
Yeah.
we did the math, we got this,
Mhm.
okay? And we said, this is not the last number. I
Right.
have to do sig figs.
Okay.
So we go back to the question. The question is, how many inches are in 2 kilometers? And so we started with 2 kilometers. How many sig figs are in 2 kilometers?
1.
There's 1. Do you see that there's 1?
Is it 1 because it's 2.0 or just because
It's not
it's
2.0. It's because it's just 2.
2?
It's 1 sig fig. If it was 2.0, that'd be 2 sig
2.
figs.
Okay.
So because we started with 1 sig fig, we have to end with 1 sig fig.
Okay. Oh, so now if I had like how many inches are in 35 kilometers, that would be 2
2
sig
sig
figs.
figs.
So you'll end up with a
Two.
two sig fig. 2,
Correct. So you would get a big, long, complicated answer
right.
that you would then round to sig figs.
Okay. So you rounded the 7, 8, 7.
We rounded there to get 1 sig fig.
Yeah, I see that. You see, I see it now. Whew. Thank
And
you.
then that's
So,
why I have to put all
On
of
the
that.
calculator, it says, 0.15 for 748. How do you know it's 0.15? Is it because of the 2.5?
That was just an arbitrary starting point, because we only needed, in the end, we were going to need 1 sig fig, and so we were going to chop it all up anyways.
Okay.
So you want to write it out and then round the one that's nothing like that.
So what determines what the final answer is in terms of 6 feet would be what we started with?
Correct. Did you get your answer question by other people, or?
Yeah.
Okay.
So is it just like preference if you want it in scientific notation or, okay, got it.
Because the question didn't say,
Mhm.
so this is just as correct as 8 times 10 to the fourth.
Okay.
Here's another one. What is the volume of a 14, I'm gonna skip this one. This one is more complicated than anything you'd have to do in a quiz or anything, okay? So if you want to do it, this is a hard dimensional analysis problem, okay? If you want to cross it out, that's fine by me. Is this the last slide? There. Dan runs 6 5Ks per year. How many inches is this?
Are we doing this on our own?
No.
Oh.
So, what number are we starting with?
Kilometers.
6
6 5Ks. 5Ks is our unit. He runs 6 of them. Okay? So he runs 6 5Ks. What is the final unit we're trying to get to? Inches. So, what unit has to go here?
K's.
Not just Ks,
5.
5Ks. What relationship do you know, it's not up here, that you think you can use? You have to get out of 5Ks, right?
I'm sorry.
Right, so what is the Ks? Well, 5Ks.
Of meters.
That's the kilometer. It's a 5-kilometer race, right? So I would say 1 5K equals 5 kilometers. If you wanted to go 5K to 5,000 meters, you could do that.
Why are you doing
Start at 30
5,000?
kilometers.
Because they go from,
Because I can go from 5Ks to kilometers, kilometers to meters. 1 kilometer is 1,000 meters. What unit goes here? Meter. And where do you think you want to go next? Yards. Because we're given a conversion factor to go from meters to yards. And so how do I use that here? What number goes here?
1.09.
1.09, and what number goes here?
1.
1. And then what unit goes here?
Yeah.
Yards. What
Inches.
number can go here? We can go feet. We might know a more direct route. You can go yards, inches. So what number goes here? 36 inches in 1 yard.
So like she asked, how come you couldn't start out with 35?
30 kilometers.
Oh,
Start out
30,
with
yeah.
6 5Ks, 1 5K. Why don't you start out with 30 kilometers?
Because if you start with 30 kilometers, you did that part in your head. That's all you did. You did this part.
So you
in your
can
head.
start out with
You can, yeah.
Okay.
It's just, if you have to be comfortable, you have to know what you're doing to do it that way. If you don't know what you're doing, you can follow the units and it'll lead you there.
So when you do this top part, when you're multiplying across, do you do 6 times 5 times 5?
6 times 5
Oh, but you
times
still
5. That 5 is part of a unit. That's wacky because I made up a stupid question. So you got 6 times 5 is 30. Yes, 30. Times 1,000 times 1.09 times 36. So does anybody do it? Is everybody comfortable doing, once you get this, are you comfortable getting an answer?
Yeah.
multiply everything on the top, multiply everything on the bottom, divide the top by the bottom, do savings. Good? Okay. We're gonna skip that last slide. And before we do the quiz, we'll go over some things. So, like I mentioned, for the most part, in terms of quizzes and especially exams, the Canvas homework is going to be your guide for what you need to know. Okay? The quizzes are going to ask you about similar